Okay, so this is the second half of 3.6, and in this part we're going to deal with the intersections of three planes this time. It's a little bit more complicated than two planes, but still we'll make sure that everything is well explained, and hopefully you'll have everything that you need to get through this stuff without any troubles. Before we start dealing with solutions, let's talk about how we classify systems of three planes. Now, with this, as you probably guessed, it's a little more complicated than two planes. In fact, there are 6 different types of solutions that we're going to go through. To help us break it down a little bit, we're going to start by talking a little bit about terminology, and we're going to start by talking about consistent and inconsistent systems. Now, consistent systems are systems where we have one or more solutions that are common to all three planes. So in this example, the very first one, we have an intersection at a single point, or we could have an intersection as a line, kind of like we saw in the first half of this lesson. Or we could have all three planes coincident, intersecting all together. So those are the 3 types of consistent solutions that we can have. Now that we've dealt with that, let's talk about some inconsistent systems. Now, if consistent systems are ones that have a solution common to all 3 planes, inconsistent systems are ones that have no solution that is common to all 3 planes. And we can have this in a few different ways. Option 1 is that we could have some parallel planes and at least 2 are distinct. Sometimes we could have 2 coincident ones, but if they're not all coincident, it doesn't work. Option 2 is that we could have 2 parallel distinct planes, but we could have a third plane that's non-parallel, but intersects in 2 different lines. And because the other 2 are parallel, we know we can't have a single solution. And option 3 for this category is that we could have 3 planes that intersect in 3 parallel lines that never meet. If they weren't parallel, then they'd have to intersect somewhere. But if they're parallel, then we know they're never going to meet. So in this case, because no one line works for all 3 systems, each line only works for 2 of the 3 systems. So that one is inconsistent as well. So now that we talked about the 6 different types of intersections, let's talk about how we classify them and how we can figure out which one is which. So the first test that we have to help us determine which type of system it is one that we used in the last part of the lesson, which is looking at the normals and seeing if they're scalar multiples. So this will help us if we look at them. So take a look at option 1. We know they're all running in different directions. They're not parallel, so they can't be scalar multiples. Option 2, again, they're running in different directions. They're not scalar multiples. Option 3, you notice that they're all coincident, so the normal is perpendicular to all 3. It should be all parallel or all scalar multiples when we look at them. Option 4, all the parallels, all the normals are running in the same direction, so we know that they're scalar multiples. Option 5, 2 of the 3 normals are running in the same direction, so those 2 are going to be scalar multiples, but the third one won't be. And option 6, they're all running in different directions, so they're not going to be scalar multiples. So the big takeaway from this, just like with the last set of problems, if they are parallel and distinct planes or if they're coincident planes, they're going to have normals that are scalar multiples. So in fact, just from looking at the normals, you can tell if it is either of those 2 options there, or if it is the third option from the first category. So in fact, just looking at the normals, you can figure out 3 of the types of intersections. But the trouble is, with the other 3, now we need a bit more information. So let's talk about one more piece of information that's going to be helpful. Now, when we look at normals, another piece of information that we look at is, are they coplanar? Now, I can't remember if we dealt with this in Unit 2, but just in case, let's talk about coplanar means. Essentially, coplanar means that all of our vectors can be fit inside one single plane. So to give you an example, let me draw 3 vectors at the side here. Now, all three of these vectors fit inside the plane of our computer screen. Your computer screen, my computer screen, whatever screen you happen to be looking at. So those would be coplanar. If one of those vectors, let's get rid of one of these and let's use your mind's eye and pretend like there's one that's shooting out of the screen. We can't fit those inside one single plane, so those would not be coplanar. So essentially, in a nutshell, that's what coplanar means. We'll talk in a minute about how to test for coplanarity. But right now, let's just look at our solutions here and figure out what our options are here. So option one, take a look. Our blue plane and our red plane have normals that kind of run in the same direction as our computer screen. But the green plane, the normal will probably shoot out of our screen. So in that case, that is not coplanar. Option two, over here, all three of those look like they're all going in the direction of our computer screen, so those ones are coplanar. So right now, if we can have a test to figure out if they're coplanar, that can help us to determine between those two. And option three is this one here. That's the only other one that we couldn't figure out using the scalar multiples of our normals. So in this case, it looks like they're all running in the direction of the computer screen, so those would be coplanar. So to summarize, first thing you're going to do always is you're going to check your scalar multiples of your normals and see if they're scalar multiples, and then you can figure out from those first three options if they're parallel, distinct, or coincident, or if it intersects in two lines, if two of them are scalar multiples and the other is not. And then we just need to take a look and see if they're coplanar. If they are coplanar, then it's going to intersect in a single line or in pairs like that last example. And I'll show you how to differentiate between the two a little bit later on in the lesson. And lastly, the big one, if they are not coplanar, the normals, then they're going to intersect at a point. So keep that cheat sheet handy. That's going to come in handy as we start dealing with some of these problems. So we said if we can look at the scalar multiple, at the normals, and figure out number one are the scalar multiples, and two if they're coplanar, that will give us most of the information we need to start classifying these planes and figure out what type of solution we need. But we don't have a test yet to figure out if they're coplanar. So in order to do that, we're going to use a little bit of information that we learned about in Unit 2, which is the triple scalar product. This little thing here. N1 dot N2 cross N3. Now, the reason why this works, let's take a look at this example off to the side, this diagram that I drew. Now we have N1, N2, N3. Now, we said with the triple scalar product, we start by doing the cross product. So we're going to take the cross product of N2 and N3. And we know that if we take the cross product, then the cross product, the vector that we generate, has to be perpendicular to those two. So right now I want you to use your mind's eye, and I want you to imagine N2 and N3, N2 cross N3, that vector, shooting out of the computer screen. Now you know that that's going to be perpendicular with normal 1. So if we take the dot product of that normal 1, it should be 0. As it turns out, that's actually a really handy way of telling us if they're coplanar, because we know that these three vectors are coplanar. So as it turns out, whenever we take the triple scalar product, if the product is 0, then the vectors will be coplanar. If the product is not 0, then they are not coplanar. In fact, that's that situation where we have it intersecting at a point. So I kind of think of that like the Holy Grail. It's the one time where we can actually get intersection at a point for these problems. So I kind of think of that one as being a little bit special. So now that we talked about that, we pretty much have all the information that we need to start classifying intersections of planes, and then we'll start talking about how to find solutions. So example 4 gives us 3 equations of planes, and it says determine if the system can be solved, then solve the system or describe it. So step one, just like with two planes, we're going to start by examining our normals like we did here. So we're going to take our three normals from our equations. Just remember, take the coefficients off of x, y, and z and plug them into a vector, and we can analyze them. Now, in this case, we know that we can't connect normal 1 and normal 2 because they're not scalar multiples. But if you look at normal 1 and normal 3, it's just, normal 3 is just 4 times normal 1, which we have summarized right here. So we're saying this is 4 times normal 1 equals normal 3, which means that normal 1 and normal 3 will be scalar multiples, but normal 2 will not. So essentially, what that's going to tell us right now is that plane 1 and plane 3 are going to run parallel and distinct, or they're coincident, like we summarized here. So they could be this coincident system here, or it could be this parallel and distinct system here. The trouble is we don't know which one yet, and one of them is going to give a solution. The coincident solution is going to be intersecting at a line, and option 2 is going to be parallel and distinct. So we're going to have two separate lines. So that one is going to be inconsistent. So right now, we've narrowed it down to one consistent possibility and one inconsistent possibility. So right now, we need to determine between plane 1 and plane 3, are they coincident or are they parallel and distinct? So again, we're going to use that same trick that we learned in the last part of the lesson, which is we're going to examine the equations. So we're going to take these and we're going to multiply them out so that way our ABC values are all the same, and we're going to check our D value. So to do that, I've taken plane 1 and I've multiplied it by 4. So now plane 1, the equation reads as 12x plus 4y minus 8z equals 48. Now if we compare the D values, we have 48 and we have -4, which means that those are not the same plane, which means that they are parallel and distinct. So now we have shown that this possibility here, and so we're going to summarize. Therefore, we have two parallel and distinct planes with one non-parallel plane, and this is going to be an inconsistent solution. Now, the other big thing I want to point out right now is that if there is a solution, we're going to find it and state at the end. If it's inconsistent, then we need to make sure that we state that, so that way we know that there's not a singular solution. If it's inconsistent, that's all we need to do is classify it and write inconsistent, and then that's the end of our solution. If it's consistent and we can find a solution, then we should find it and state it. Let's go on to problem 5. Again, it says determine if the system can be solved, then solve the system or describe it. So before we do anything, we're going to take our normals and we're going to write them out, and we're going to examine them a little bit. So in this case, we have 1, -5, 2, 1, 7, -2, and 8, 5, 1. In this case, we cannot find any scalar multiples in there, so they are not scalar multiples, which means that we have no parallel or coincident planes. So we've already eliminated 3 of the options. Now we have to start narrowing it down a little bit more. So now that we've looked at the normals and seen if they're scalar multiples, next let's test and see if they're coplanar. So we're going to take the triple scalar product of those 3. It doesn't matter which normal you put where, as long as they're all in there somewhere and you do them in the right order. Start with the cross product, and then take the dot product. In this case, if you do all the math correctly, then you should get 0 as the result. And we said according to our tests, if it is 0, then they are coplanar. So we said there are only 2 options for systems with coplanar planes or coplanar normals. So it means that they're going to intersect at a single line, or they're going to intersect in pairs. So again, we have one consistent solution where we can have one single line, or we have an inconsistent solution. Now to help us to figure out which one, we're going to use a little bit of a math trick here. So I want us to, let's take that first example where we have three intersected line, but let's pretend like that one of these can shift a little bit. You can shift it down here. So really, that's all that's happening here. We're just not sure if that third plane is lining up so that way we get an intersection at a single line. So what we're going to do is we're going to, just like we did in the last part of the lesson, we're going to take those other two planes and we are going to find the line of intersection between those to start. And then we're going to try and figure out if that line fits in with the third plane. So to start this, we're going to just, in our solution here, we're going to start by just taking the first two planes and ignoring the third one to start. And we're going to, just like we have with two planes, we're going to find the line of intersection. We're going to start by eliminating a variable. So in this case, it makes the most sense to get rid of z. So that's what I did. I added them up, and we get 2x plus 2y minus 4 equals 0. Or we simplify that, and it becomes x equals 2 minus y. And again, just like before, we're going to set one of our variables equal to t and start making parametric equations. So if, in this case, it makes sense for y to be equal to t because x is already by itself. So x becomes 2 minus t. We just replace the y with t in the equation that we found. And lastly, we take one of those two planes, not plane 3 because we're ignoring it right now. And we're going to sub in those two parametric equations. And when we rearrange all of that, it becomes z equals 4 plus 3t. And again, this is just the same idea that we did in the first part of the lesson, where we're just finding the intersection between those two planes as a parametric equation of a line. So now that we have all three of our equations, we've summarized that down here. So now we have an equation of a line that intersects plane 1 and plane 2, but we don't know yet if it's going to intersect plane 3. So to do that, what we're going to do is we're going to pick a point on plane 3, and we're going to test it. Into our line. Actually, scratch that. We're going to do the opposite. We're going to take a point off this line, and we're going to test it in plane 3. In fact, I think you could probably do it either way, but just so it matches my solution here, let's test a point here. Now, looking at our solution here, we have 2 minus t, y equals t, and 4 plus 3t. And I want you to use your mind's eye and just imagine that as an equation of a line in vector form. Our position vector there is just going to be all of the constants. That's going to be 2, 0, because there's no constant for y, and 4. So that would be the position vector if we were to put it back into the vector form of our equation. So we're going to take that point, and down below, we're just going to sub it in to equation 3. And if that point from the line fits in on plane 3, that means that the line has to be inside that plane as well. So in this case, by subbing in the point into the plane, we're making the assumption that the point fits in the plane, and we're going to see what happens. When we simplify this, we get 0 equals 0, which means that we know that to be universally true, so it means that our assumption was correct. So our assumption being that the point on the line, 2, 0, 4, fits in the plane. So that means the point fits in the line, which fits in the plane, which means that that line is common to plane 1 and plane 2, but also plane 3. So lastly, we're going to conclude, and our concluding statement is going to be all three planes intersect on the line x equals 2 minus t, y equals t, and z equals 4 plus 3t. Let's go on to example 6. It asks us to, again, determine if the system can be solved, then solve the system or describe it. So just like before, we're going to start by examining the normals, and if we need to, start testing for coplanarity. So start by looking at the normals. In this case, they are not scalar multiples, so we know that they have to be either parallel or coincident, just like the last problem. So basically, the method's going to be the exact same. Oh, sorry, I'm jumping ahead of myself. Right now, all we've shown is that they are either parallel, they're not parallel or coincident. You could still have that intersection at a point. So at this point, to help narrow it down a bit more, we're going to test for coplanarity using the triple scalar product. So we just plug in normal 1, normal 2, normal 3. We solve by starting with a cross product and then doing the dot product. In this case, again, we have a dot product, triple scalar product of 0, which means that we're either going to have intersection in pairs or intersecting at a line. So again, same basic method as last time. We're going to use the same method to help figure out which one it is. So again, we're going to take two of the planes. Again, let's start with plane 1 and plane 2 because it's pretty easy to get rid of those z's. And we're just going to use elimination to get rid of the z's. Then we're going to start making our parametric equations, and the math in this one gets a little bit messy. So I'm going to fast forward through it, and hopefully it should hopefully make sense, but the method's going to be the same. And then we take those first two parametric equations, we plug them into either one of our planar equations, 1 or 2. And when we do that, we rearrange and we get an equation for z. So now we have an equation for all 3 points. And again, from that, we could try and use the position vector from that, but some messy fractions. It will work for you. But in this case, we can use one other trick, which is we can just use a parameter and plug that in to help find a point. So we're going to use t equals 2, and we're going to plug that into our 3 equations. And you're going to see the result below. So we start, if x equals t, then x is equals 2 in this case. For y, we plug 2 into that parametric equation, we get -2. And for z, it equals 6. And again, you could just use the position vectors if you'd rather, but it's going to make the math a little bit messier, so it's up to you. I'm just going to show you this one other method. In fact, with the position vector, we're essentially just doing the same method, except in that case, in the last problem, it was really just t equals 0. We just plugged 2 minus 0, y equals 0, and 4 plus 3 times 0. So essentially, we're doing the same thing, except we just had a parameter of 0. So either method will work for you. Just use whatever one makes the most sense, and it's going to make your life easier. But either way, we said we need to find that point on the line between 1 and 2 and see if it works in plane 3. Because if it works in plane 3, it means that our line is common to plane 3 as well. So in this case, we plugged it in, and then we find that we get a result of 16 equals -4. So that's a nonsensical answer. So it means that our assumption that this point fits in the plane is incorrect. So if the point doesn't fit in the plane, then the line doesn't fit in the plane, which means that we cannot have a common intersection between all 3. It means that we are looking at the intersecting in pairs option. So we're going to have 3 different lines that make up our intersection here. So in this case, we don't. If we have more than one solution that's it's inconsistent, we don't have to go any further. We can just say intersecting in pairs is inconsistent. All right, so we have one more example here. And again, it says determine if the system can be solved, then solve the system or describe it. So we're going to start as usual, examine the normals, write them out, take a look, see if we have any scalar multiples in the bunch. And in this case, we have no scalar multiples, which means we can have no parallel, distinct, or coincident planes. So now we've gotten rid of 3 of the options, but we don't know, we need to narrow it down more. So in this case, we need to test to see if our normals are coplanar. So we're going to find the triple scalar product of all 3 normals. And in this case, I'll leave you to do the math, but if you do it correctly, you should get negative 65, which we know not to be equal to 0. So in this case, it's not coplanar. And we said if it's not scalar multiples, not coplanar, this is like the Holy Grail. This is where we have the one singular solution at a point. So we're going to learn the last method now to solve for an intersection at a point. So just like before, we're going to use elimination, but because we have to solve at a point, it looks a little bit different. But again, it's all based out of elimination. So first thing we have to do, number one, we're starting off with 3 equations with 3 variables. So this is really, really way too many variables and way too many equations to work with. In order to use elimination properly, we need to have a system of 2 equations and 2 variables. So our first step is we're going to use a bit of magical trickery to help us get this down to 2 equations with 2 variables. So what we're going to do, the first step, we're going to use elimination to help get rid of some variables, and we're going to do it with 2 different pairs. So it doesn't matter which pairs you pick as long as they're not the same 2 planes both times. The first one, I'm picking plane 1 and plane 3. And option 2, I'm picking plane 2 and plane 3. And what we're going to do is we're going to use elimination to get rid of the same variable in both. So an example, in part 1, with plane 1 and plane 3, I've multiplied plane 3 by 2, and then we can just subtract off the x's. So now we're left with 5y plus 14z plus 11 equals 0. So now we have one equation with just y and z, no x. So now that we have that, let's look at the second system of equations. Now we're dealing with plane 2 and plane 3. And again, we want to get rid of x because if we have 2 other variables that aren't y and z, it's not going to help us very much. We need to have y and z, so now we're stuck. We need to get rid of the x's. So we're going to take our plane 3 and we're going to multiply it by a factor of 3, which brings up to 3x. We just need to make it the same coefficients, so that way they'll subtract out. So wherever you need to multiply to get your x coefficients the same, that's what you're going to multiply. So now that we've done that, we're going to subtract the 2 planes, and we get 0x plus 10y plus 5z plus 35 equals 0, or we could just divide everything up by 5, and we get 2y plus 3z plus 7 equals 0. So now that we have that, we have 2 different equations. We're going to call them, let's call them 4 and 5, just to make things simple. And you notice how those 2 equations just have y's and z's. And we know that if we have 2 equations with 2 variables that are the same, we can just use substitution or elimination to solve. You can use whatever method you want. I used elimination just because we seem to be doing a lot of that right now. So we are taking equation 4 and equation 5, and we're going to use elimination to solve. To do this, we're going to multiply. Let's get rid of the y's. So we're going to multiply equation 4 by 2 and equation 5 by 5. And when we do that, we get 0y plus 13z minus 13 equals 0. Or 13z minus 13 equals 0. And we rearrange that. It boils down to z equals 1. So now we have z equals 1. Essentially what that means is that's actually the z-coordinate for a point of intersection. So we're actually a third of the way to our solution. Actually more than a third, because after this it gets really easy. Now that we have that, now we can plug that back into equation 4 or equation 5. You can pick whichever one you want, just basic elimination, back to grade 10. And you're plugging that in. I plugged into equation 5, and that becomes 2y plus 3 times 1 instead of z, plus 7 equals 0. You rearrange, and we get y equals negative 5. So that y equals negative 5 is the y-coordinate for our point of intersection. So now we're 2/3 of the way there. So now we just need to find our x. And in order to do that, we can't use 4 or 5 because we got rid of the x's. So you can use 1, 2, or 3 to help you solve. And again, you can use whichever one you want. I'm going to pick plane 1, which I've done down here. So essentially, we're just taking plane 1, and we're going to sub in that y and that z, and we're going to see what our x value is. And when we do that, we get a result of x equals 3. And again, you could use any plane you want, 1, 2, or 3, and they'll all give you x equals 3 if you've done it correctly. And in fact, you can use that as a good test. Once you've found your point of intersection, you can test it in all 3 planes if you really want to make sure that you got it. So lastly, if you have all 3 of your coordinates, all you have to do is conclude with your point of intersection. So therefore, the point of intersection is 3, negative 5, 1. And again, don't forget to use round brackets because it's a point, not a vector. And the last thing I'll mention with this is, in this case, because it's a point of intersection, it's kind of implied that it's consistent, so you don't need to state it. If it's inconsistent, then you really need to make sure that you state it. If you have a solution, you can state that, and that's sufficient. Okay. So that is pretty much it for intersections of planes. Hopefully that it all makes sense. If not, come and see me in our video chat, and I'll help to sort things out, or shoot me an email, and we'll get things sorted out. Make sure you do lots of practice, because it's one of those things that the more you do, the better you get. And the last thing I will mention, there's one other method to solving for point of intersection. It's totally optional. If you're happy with this, then feel free just to leave it at that, and go on with your life. If you're interested, I will post the notes separately in the OneNote, and I will post a video as well. So that's pretty much it for intersection of planes. Very last thing, we are now done vector geometry. Please give yourself a big pat on the back. We've made it through. Just do the practice, get through the last couple of assessments, and then we are on to calculus. Congratulations.